In this video, we're going to be discussing Lab 8, Law of Definite Proportion. And Law of Definite Proportion is a lab that deals with the composition of a compound, all right? So the composition of a compound is always going to be a constant, okay? So the elements in the compound are going to be combined in a definite ratio, all right? And that's never going to change no matter where the sample of that compound is, okay? For example, water. 1 mole of water, there will be 2 grams of hydrogen, 16 grams of oxygen. So 16 plus 2, 18, all right? So 2 by 16th or 1 by 8th of the mass of water is going to be, 2 by 18, that is 1 by 9th of the mass of water is always going to be hydrogen, that's 11%, and then the rest, the 89%, is oxygen. Now the same thing if you look at sodium chloride, okay? A mole of sodium chloride, 23 grams out of the 58.5 is sodium, all right? So that's about 39%. And the rest, the 61%, is the chloride, okay, or chlorine. And so those proportions are never going to change. They also indicate a pure substance. Pure sodium chloride would have these percentage by mass of each of the component elements, all right? Same thing with water. You can have water which is spring water or tap water, as long as it's pure water. Tap water tends to be impure, but maybe some other pure distilled water, all right? Then they're always going to have that percentage composition of hydrogen to oxygen of 11 is to 89, all right? So that's how you can identify this substance called water. And so we're going to be applying that law here in this particular experiment. We're taking potassium chlorate, KClO3. Now from the formula it indicates there's 3 oxygens in KClO3, okay? Now if you take this compound and you heat it, it breaks down, it decomposes, and when it decomposes, it and this triangle signifies heat, all right? So when you're writing the equation for this reaction, that's what it means. If you heat this compound, it breaks up and it forms potassium chloride, okay? So it breaks up literally like this, the potassium chloride, and the oxygens come off in the form of gas, okay? Now if you had the mass of the potassium chlorate to begin with, okay, after the reaction, the total mass of that oxygen and potassium chloride should equal the mass of that potassium chlorate, okay? Because of the fact that mass or matter cannot be created or destroyed, which also relates to the fact that atoms cannot be created or destroyed. As you can see, in a reaction, they're just getting rearranged. So if you take the mass of the reactants, they should equal the mass of the products due to the law of conservation of mass, okay? Now oxygen is a gas, so it can escape into the atmosphere unless the reaction vessel is a closed system. Then you can kind of trap the oxygen in that reaction vessel, okay? So in this case, an open system would allow that oxygen to escape. So the mass of the product is going to be less than the mass of the reactant because of the fact that the oxygen has escaped, right? So going back, you will see that if you start out with a certain mass of the potassium chlorate, because the oxygen has escaped, what's left, which is the potassium chloride, which is a solid, it's going to be left behind. So this mass after the reaction, after the escape of all of that oxygen, is going to be less. So the final mass after the reaction is going to be less than the starting mass. Okay, so what you're going to do is you'll subtract the mass of the potassium chloride from the mass of the potassium chlorate. So if you take out the mass of these two, then you should get the mass of the oxygen, all right? And that's what you're going to be doing. So then once you have that mass, you'll calculate the percentage by mass of oxygen in the original potassium chlorate. Okay, so this would be your experimental value for that percentage. You can also calculate by theory, since you know that in the formula there's 3 oxygens, all right? So oxygen is 16, so 3 times 16, about 48 grams of the potassium chlorate is oxygen. So you can calculate the percentage by mass of oxygen in the potassium chlorate. Now once you have those, the experimental percentage mass for oxygen, the theoretical percentage mass of oxygen, you can compare those two values to see how close you are and to see whether how successful your experiment was. So you're going to take a crucible. So anytime you heat something really high, you would take this container called the crucible, all right, a white container, and then and bring a Bunsen burner onto your workbench, and then place that. First, weigh the crucible, all right. To it, you're adding some manganese 4 dioxide, all right. So manganese 4 dioxide. This is a catalyst. It'll help to speed up the reaction, all right. Just heat alone may not be enough to break this down. With the help of the catalyst, it's going to go a lot faster. So you're going to add 1/10 or 0.1 grams of the catalyst, and then weigh that crucible, all right. So it will be the crucible plus that catalyst. That will be your first weight, and then you're going to also add to it your 20 grams of the potassium chlorate, okay. And then you're going to record that mass of the crucible and the contents, all right. Now bring that Bunsen burner under this, place this crucible and contents over the Bunsen burner, and then have it on a low flame and heat the reactant, which is the 20 grams of potassium chlorate, for 2 minutes. So you can use the timer at the bottom of your screen, or you can use your cell phone timer, okay. And when you heat it for that 2 minutes, what will happen is you'll allow all of that oxygen to escape out, leaving behind the potassium chloride, okay. So if you take the mass of this and you subtract it from the mass of the potassium chlorate, you should be able to get the mass of the oxygen. So once you've done this heating step, you cool and then weigh it, all right. If that mass has not come down, then you can reheat it again for another 2 minutes, then cool it down and weigh again. So the initial mass for the crucible with the catalyst was 88.10, okay. And then the mass of the crucible, the catalyst plus that KClO3, the 20 grams of KClO3, is 108.10. So if you subtract that 88 from 108, it'll give you 20 grams. That's the amount of KClO3 that you took. Okay. Now, what you're going to do is do the heating step, cool, and then reweigh it. And then when you do that, you can see that the mass has come down as it should. All right. So right now, it's just going to be the crucible, the catalyst, which doesn't get destroyed, and then the KCl. All right. So that's 100.267 grams. Now, if I subtract this number from this number, I get the mass of the oxygen that escaped out. So that's 7.833 grams. Okay. What's the mass of the KCl? It would be the 20 grams of KClO3 minus the mass of the oxygen, and that would give me the mass of KCl. Okay. Okay. So if I take out the mass of the oxygen, what I'm left with is the mass of the KCl. Okay. So the mass of the oxygen loss from my experiment is 7.833. The mass of the initial KClO3, the reactant, is 20 grams times 100. So 39.17% is my percentage mass for oxygen. If I try to do this by theory, all right, so 3 atoms of oxygen, that comes to 48 grams. If I take the molar mass of KClO3, that's 123 grams. 48 divided by 123 times 100 gives me 39.17%. So my experimental percentage mass for oxygen and my theory percentage mass for oxygen are identical. Okay. So the percentage error, experiment minus the theory divided by theory times 100, okay, and it's 0. Now, this is an absolute value because this is a percentage, and this is also a percentage, okay. So there's no plus minus, it's just that whatever number that you get, it's always going to be positive and absolute value, okay. All right. So in my case, it's 0% because both theory and the experimental value match. So what was the aim of this? The aim was to illustrate the law of definite proportion and to find the percentage of mass of oxygen in my sample, 20-gram sample of potassium chlorate, after breaking it down or decomposing it to potassium chloride and oxygen gas. My hypothesis is that the amount of oxygen lost would be close to that 7.75 grams, which corresponds to approximately 3 atoms of oxygen in a 20-gram sample of potassium chlorate. All right. Now, it could be less than the expected amount, but if I'm doing my experiment correctly, it should be close, right? So I list all my materials, equipment, procedure, write up my procedure, and then my observations, which is my data table, and then my results, which shows that my experimental percentage and theoretical percentage are exactly the same, and my percentage experimental error is 0%. So the results showed that both the experimental and theoretical percentage mass of oxygen were exactly the same, all right? And thus my proposed hypothesis is confirmed, showing the law of definite proportion. So what did I learn from this experiment? What I learned that compounds are made up of atoms combined in fixed ratios, all right? It's always a 2-to-1 in water of hydrogen and oxygen, whereas a 1-to-1 in hydrogen peroxide. So the percentage of oxygen by mass in hydrogen peroxide is 96% as opposed to 88% in water, all right? So